So our first talk is going to be a PhD student in our group, Osman Sarood. He's going to talk about how Charm handles energy awareness and how its load balancing mechanisms allow constraining core temperatures.
How to reduce total energy consumption? So the total comes in because we have cooling energy consumption. This part of research is focusing on machine power energy consumption, so reducing machine energy consumption, constraining core temperatures. So although I don't think we need a lot of motivation, it's all over the place, because in order to move to extra scale, we definitely need to have good mechanisms to save energy consumption. But still, I'll share a few figures. So data centers in year 2006 consumed 2% of the total US energy budget. Their operation costed $4.1 billion and they consumed energy equivalent to 59 billion kilowatt hours. According to some studies, 3G's cost of powering and cooling servers exceed the cost of purchasing the server hardware itself. And so why are we considering core temperatures? It turns out that cooling energy accounts for a significant part of the total data center cost. It turns out that it forms 40 to 50% of the total cost for a data center. And most data centers face the issue of hotspot, which is mainly responsible for keeping very low temperatures in the entire machine rooms. According to studies, data centers can save 7% of total cooling energy consumption by just increasing the machine room temperature by 1 degree centigrade. Not only that, they can save 50% of the total cooling energy cost by increasing the machine room temperature from 20 degrees Celsius to 27 degrees Celsius. In our earlier work, we have shown that we can reduce cooling energy by 63% with an execution time penalty of only 11% if we constrain core temperatures for below 44 degrees Celsius for that particular machine. This part of work concentrates on saving or reducing machine energy consumption, which forms 50 to 60% of the total data center cost. In our earlier work, we did end up saving machine energy cost, but it was very limited since it wasn't concentrating on only saving machine energy consumption. Its main emphasis was to save cooling energy cost. So now we ask the question, is it possible to reduce execution time penalty and machine energy consumption while constraining core temperatures? So we'll still keep on this constraint of constraining core temperatures, since the idea is to combine both the techniques and save both cooling and machine energy cost. This figure shows average temperature for 4 of the NPB benchmarks over a period of 20 minutes. And these results were obtained from a quad-core machine having Sandy Bridge Core i7 chip. And you can see that the core temperatures, the steady state core temperatures for different applications vary a lot. And the whole point of this study is to evaluate the impact of constraining core temperatures on different applications.
Can you say that integer sort ran for 1,000 seconds? Or are you just running it repeatedly?
We are running most of these applications repeatedly. So we are using it like to repeat them again and again. So in order to see the relation of execution time and core power consumption, we ran NPB-FT for 4 different frequency levels. And the reason that we chose core power consumption is that the core temperatures are mainly dependent on the power that is dissipated inside the cores and the CPU, and it does not directly depend on the total machine power consumption. And we can see from this figure that as we go on decreasing the frequency, the execution time does not increase by a lot, but there is a significant decrease in the core power consumption. So this basically means is that if we run the same application at a lower frequency, we would not increase the execution time by a lot, but we can significantly reduce core power consumption, which basically means that we will reduce the energy consumption for the cores, which in turn can result in lower core temperatures.
By the way, did you also look at energy, not just watts?
Yeah, that will come later in the talk. This is just to show the motivation that something can be done about it.
Okay.
So we implemented a Naïve scheme where we monitored temperatures periodically, and if the core temperature. So in order to constrain core temperatures, we implemented a Naïve scheme which basically monitored core temperatures periodically, and whenever the average core temperature was above a certain threshold, we decreased the frequency for the entire chip, and whenever it was below the specified threshold, we increased the frequency for the entire chip. And just to mention that we used dynamic voltage and frequency scaling in order to change processor frequency and voltage at runtime. We ran this scheme on NPB-FT for different temperature thresholds. So we repeated the same run for all these different maximum temperature thresholds, and this figure plots the timing penalty in execution time, which basically refers to the increase in execution time because of working at lower frequencies triggered by the core temperatures exceeding the threshold. And on the second axis we have energy savings. So from this figure it's quite clear that we can save a lot of machine energy consumption, but it carries a significant execution time penalty, which for the 46 degrees Celsius case goes up to 30% of the execution time. So now we ask the question, can you do something to reduce the execution time penalty? And it turns out that the idea of execution blocks, which basically means that we divide an application into different sections according to their sensitivity to frequency. This idea has been explored by other HPC researchers as well, and the entire idea is, as shown by this block diagram, that for each iteration we divide it into multiple execution blocks depending on the sensitivity to frequency. And this would be more clear if we consider the following case. So we ran a few experiments using integer sort from NPB suite, and we first divided the integer sort to two different parts, which is represented by EB1 and EB2 over here, and we did a series of experiments where we changed the frequency and ran the same experiment again and again, recording the execution time taken by each execution block and the core power consumption for the same blocks. And we can see from the red curve that EB1 is very much dependent on frequency, or we can say that it's very sensitive to frequency, as a decrease in frequency causes a significant increase in the execution time. On the other hand, EB2 is barely sensitive to frequency, and even at the lowest possible frequency it hardly takes any longer. But the surprising thing over here is that the core power consumption for both the EBs is almost the same, which basically means that running EB2 at the maximum frequency is wastage of energy, because you can run the same execution block at a lower frequency and still not suffer an execution time penalty. Yeah, surprising in the fact that at least I earlier believed that if you are not seeing any difference in execution time, the processor would not be using the resources that much, and it should not consume a lot of power, which is actually true in some cases. For example, if you compare the core power consumption for integer sort to, let's say, NPB LU benchmark, there is a significant difference. So using the motivation from the last slide, we came up with the following approach. We profile each execution block for all frequency levels, and the reason that we used Intel's new Sandy Bridge chip was that it supports energy consumption statistics on which are provided through the machine specific registers residing on chip, and using that we profiled for all frequency levels in order of milliseconds, which is much better than what most HPC researchers have done earlier. And over here the idea is that if the core temperatures exceed the specified threshold, we only reduce the frequency of the execution block, which results in the minimum timing penalty. And if the temperature is less than the threshold, we increase the frequency of the execution block that results in the maximum execution time reduction. And just to formulate the problem, we need to minimize the execution time subject to the constraint that all core temperatures are below the specified threshold, and for our scheme we use the following heuristic, which basically says that we take the difference in power consumptions after reducing the frequency for execution block I, and we take the difference in execution time after reducing the frequency for execution block I, and we try to maximize this ratio in case the temperature is greater than the threshold. And in the other case where the temperature is less than the threshold, we try to minimize the same heuristic or the same ratio. So to give a bird's eye view of how this framework works is we have a profiler which profiles all EBs for all frequency levels in matter of milliseconds, and then it proceeds on to the application itself. And before each EB there is a frequency control part which basically changes the frequency of the processor to whatever is specified for the following execution block. Once that is done, the runtime checks the temperature, and according to what the temperature is, it uses the mentioned heuristic and determines the new frequencies for each execution block. And so this check can be done at whatever the application, whatever the user wants to run it. So you can change the periodicity or basically the time after which you want to invoke the temperature check. In order to evaluate our scheme, we ran it on a single quad core machine, and the metrics that we considered for evaluating the scheme was basically the ability to constrain core temperatures, the execution time penalty for our scheme compared to the Naïve scheme, and the reduction in energy consumption. This figure shows the average temperature for all 4 applications running for 140 seconds. Well, actually they ran for much more than 140 seconds, but because it always stayed close to the temperature threshold, and in order to show the differences in the temperature gradients for different applications, we are not showing the entire time. So the interesting thing over here was that irrespective of how high the temperature gradient is for any application, our scheme was effectively able to constrain it below 54 degrees Celsius, which was the threshold in this case. In order to see its benefits in terms of execution time penalty, we plotted the increase in execution time compared to runs with no temperature control and all cores working at a maximum possible frequency. So basically this figure of 5% means that using the Naïve scheme, it took 5% more time as compared to a run with no temperature control and all cores working at the maximum possible frequency. So from this figure we can clearly see that our scheme was much better in terms of execution time in the sense that the pink bars are much lower, which signify savings in timing penalty. A few interesting observations that we made during our results was related to the steady state frequencies, and this graph shows the average frequency for all execution blocks over a period of 10 minutes. And irrespective of all applications settling to the threshold temperature of 54 degrees Celsius, we saw that all applications settled to a different frequency level. Especially, there was a difference of 400 megahertz between FT and LU, which we hypothesized is basically because of the higher amount of data transfer going on in case of FT as compared to LU. So because of more data transfer inside the chip, the caches dissipate a lot of heat, and that causes it to go to an even lower frequency. The other key observation was that despite LU running at a higher frequency, close to 2.6 gigahertz as compared to 2.3 in case of FT, the timing penalties suffered by both of them were the same. And this is basically because LU is more flop based, and it requires more computation power. So that is why even a smaller decrease in frequency results in a larger timing penalty as compared to FT. To see the impact of our scheme on different applications and to find a way of predicting how our scheme would perform for different application, we came up with this index sigma frac, which basically says the variance in sensitivity to frequency for different parts of an application. So basically an application which has which we divide into, for example, if we divide it into 2 execution blocks, and one of them is very sensitive to frequency and the other one is not at all sensitive to frequency, we should expect a higher value for sigma frac. And we found out that this value of sigma frac did tell us something about the effectiveness that we should expect using our scheme. The average reduction in timing penalty over here basically shows the benefits of our scheme as compared to the naive implementation of temperature control, and we can see that a higher value of sigma frac is coupled with a higher value for average reduction in timing penalty, which basically means that applications which have execution blocks that are more distant, in the sense that one is more sensitive as compared to the others, we should expect our scheme to perform better. In order to see how each execution block behaves during a run, we ran NPB integer sort after dividing into two execution blocks, and plotted the frequency at which each of the execution block ran, and also the frequency for the average frequency for both of these execution blocks. And we also are plotting the frequency at which the naive implementation ran. And the interesting thing over here is that although the frequency in case of the naive implementation was higher than the average frequency in case of our scheme, we ended up having a much smaller timing penalty as compared to the naive scheme. So this is basically because our scheme increases the CPU utilization, which is reflected in a higher value for the MIPS. And the reason for this is that since our scheme runs EB1 at higher frequency, and we earlier saw that EB1 was significantly dependent on frequency, our scheme is basically allocating resources to those part of an application which rely heavily on frequency, and that's the main reason we end up increasing the MIPS and the CPU utilization as well. We now will talk about the machine energy savings that resulted from our scheme, and for these three applications, FT, LU and integer sort, our scheme saved more energy as compared to the naive implementation. But in case of SP, our scheme was in most cases a little below what naive implementation did, and the reason for that is the lower value for sigma frac of 0.19 over here, which basically means that in case of SP, we were not able to identify regions that had different sensitivities. So most of all three regions which SP was divided into were almost equally sensitive to frequency, and that was the main reason our scheme was almost the same as the naive implementation.
But not the same, it's slightly worse. Is that slightly worse?
So it's slightly worse because our scheme is trying to minimize execution time. So if you see, the machine energy consumption for some of the temperature thresholds over here is less than what the naive implementation saves. But on the other hand, if you look at the execution time penalty, we do end up reducing the execution time penalty. So basically what is happening is that the ideal frequency to save maximum energy consumption for SP is much lower than what our scheme ends up running it at, because we are focused on running it at with the minimum timing penalty. So these figures over here show the normalized execution times plotted against the normalized energy. So we are basically representing the same data from the timing execution time penalty plots and the savings in machine energy consumption on these plots, and we can see that our scheme EB tuner lies to the left and below the naive implementation scheme. So a movement towards the left basically signifies a reduction in energy consumption, and a movement down represents savings in execution time. And we can see some correlation in between the sigma fracs and the gap between our scheme and the naive implementation. Like in this case, the sigma frec is 0.53, and there is a significant difference between both the schemes, and you can see the same difference here as well. But in case of SP, both the schemes are very close to each other, and we have a lower sigma frec for it as well. Although we cannot say that there is a strong correlation, because we only have 4 points to make this claim, but our results show that there was some correlation between the sigma frec index and the benefits that we can get using our scheme. And in the end, I'd like to summarize that our scheme was consistently better than the Naïve version in terms of reducing execution time penalty and machine energy savings. Using our scheme, we were able to reduce machine energy consumption by 17% with less than 1% timing penalty while constraining core temperatures below 60 degrees Celsius. And so basically what this means is that whenever you run this application on the machine that we ran on, at the maximum possible frequency without temperature control, you are basically spending 17% more energy than what you should, and this figure does not include the cooling overhead. And according to estimates, you can safely say that 30% of or actually 40% to 50% of this figure can be associated with cooling energy consumption as well. So basically we can say that we can save 25% of total energy consumption by only giving up 1% on the execution time. And in future we plan to combine this work with our earlier work, where we used load balancing to cater for multiple node case. And any questions?
Any questions?
So Usman, how agile is this scheme? You showed in your graphs that, well, let's say the saturated or steady state frequency is the right frequency at which you should run some execution block. Mm-hmm. How long does it take the tuner framework to get to that frequency?
Yeah, that's a very interesting question. So actually, it depending on the application, it can take different time. And if I just go back a little, so for example, in this in integer sort case, you can see that it took around 200 seconds to get to the sort of steady state frequency. But we also experimented with a scheme where, based on what we did was, the temperature curves that I showed at the very start of the presentation, we used a few plots and we came up with a temperature curve, a temperature curve for a specific machine, and we fed that curve to our scheme, and it basically predicted the steady state frequency. That was it worked very good in the sense that it predicted the correct frequencies, but it would not result in any execution time savings, because, and well, actually not only that, this way of reducing the frequency by one step at every time step is better in the sense that the execution time, you give the application the maximum time to run at a higher frequency level and still not violating the temperature constraint which results showed. If you use that scheme, you will straight away shift to the minimum, the optimum frequency, and you will be running the application at a lower frequency for much longer. And because the decrease in frequency would be so large, the temperatures would fall much below the threshold, and then they will start to get towards the specified threshold.
So this would be better focused towards iterative applications, right? Not something like sort,
yes,
unless you're doing it every iteration,
yes.
I suppose. Okay.
Any other questions?
Two quick questions. The first is, do you think you understand when you got good performance, when you got good energy savings, and when you didn't well enough to write a preprocessor that just determines what the frequency should be?
So you're talking about before running the application, we should determine.
So if you take your work and you really understand when you're getting savings and when you don't, mm-hmm. that expert knowledge that you have, could you just write a compiler preprocessor, use rows, something like that, and just select what you think is the right Do you know it?
Okay.
Do you understand the performance well enough to be able to figure it out rather than experimentally poke?
Okay, so that is something which, first of all, is very difficult to do, because core temperatures depend on more factors than at least I can even think of working with it for the last 2 years. In this work, I realized that it is heavily dependent on the amount of traffic going on between the cache, and there are much more factors that can affect core temperatures. So my straight answer would be that it would be very difficult to come up with something like that you get a few statistics. For example, I think
Say if you can predict cache miss rates,
Then we can predict this. At least the first order of approximation.
you can approximate it. You can say that, okay, the general trend would be to choose a frequency in between this range, but you cannot pinpoint that, okay, select this frequency, because it is dependent on the cache miss rate as well as the flops, and there are other factors which I might even not know.
Your second PhD.
Sorry?
Your second PhD. One last question. Can you imagine a case where managing the frequency and voltage would increase performance?
So basically, you mean to say that decreasing the frequency would increase the performance? It can be possible in a few cases. For example, if you are running a workload, I'm just talking based on this feature in Intel processors of Turbo Boost, and that Turbo Boost feature is dependent on the amount of power it's consuming and the heat being generated and the core temperatures. So as I showed in one of my slides, that running integer sorts second execution block at a higher frequency would dissipate a lot of power and raise the core temperature for no reason. So if you run that at a lower frequency, that would consume less power first of all, and it would not increase the core temperatures, thus allowing the Turbo Boost feature to run at the maximum possible frequency for much longer. That's one thing that I can think of right now.
Just a quick extension. So maybe if not, just as a quick extension to one of the previous questions. So maybe if not a pre-compiler, what about, say, a profiler? Especially since in a lot of your charts you're reaching a steady state over time. What if you actually kept profile information between runs?
So currently your scheme is also based on profiling. So basically there are two methodologies that we can take. One is doing some profiling for hardware counters and then predicting on their behalf. Based on them. The other one is to explicitly profile execution times and power consumption, core power consumption, and predicting based on them. So the earlier scheme based on hardware counters works well in the sense that you don't need a lot of profiling, and there are a lot of problems, a lot of complexities associated with profiling execution time and power consumption. So the hardware counter schemes does not rely on them, and it's less dependent on other things, but most of people that use them end up having a much inferior performance as compared to profiling using actual execution times and power consumptions.
He's trying to say it's just seeing results across.
So you're saying you're storing results for multiple applications and using them? So
accumulating wisdom across multiple runs of this thing.
Yeah. Actually, we need to move on. Any other pertinent questions?
Okay, let's time this one.